Hi, my name is Ryan Lewis, and welcome to another episode of the world's most rich and compelling data science podcast, Training Data by CosmicWorks. With me, I've described him this as once before, and I think it's fair to say I can describe him that once again. The Grand Meister of computer vision, Dr. Adam Van Etten. Welcome. It's great to have you back. All right, today we're going to be talking about our most near and dear topic to our hearts, and that is SpaceNet. Right. So for those of you who have not listened to our pods or looked at our blogs or websites or just checked any of our social media, SpaceNet is a collaborative effort between us, CosmicWorks, AWS or Amazon Web Services, Maxar, and Intel AI. I'm repping their Intel AI DevCon shirt today. And it is specifically focused on accelerating open source applied research for geospatial analytics. And as a part of that effort, over the course of the last 3 years, we have developed and open sourced highly curated labeled data sets of satellite images, specifically focused on foundational mapping. So this includes, as Adam's going to talk about today in greater detail, both building footprints and roads. It also includes hosting open data science competitions on Topcoder. To date, we've hosted 4. Specifically for today, we're going to be talking about our fifth and most upcoming competition, which is on road networks and routing and time, which is really cool. And then last but not least, we open source those results from the competitions. And so really just to kind of jump right in. So Adam, in our previous pod, we talked about SpaceNet 3, which was our first foray into looking at road network and routing from a single satellite image. Why do we care about that? Well, I know we've talked about this before, but why don't we just do a brief rehash of that for those who perhaps haven't listened to a previous pod or read any of our material before?
There we go. Hey, all right, yeah. So as you probably know, our first couple challenges were building footprints, and we had some pretty successful results there, and that was pretty exciting. And I think the next obvious step for us was to look at roads. And people have looked at roads from satellite imagery and overhead imagery before, and had some success, but those approaches in the competition sense were typically looking at pixels. So you have an image and you try and figure out which pixels belong to roads, which pixels belong to backgrounds, and then you score yourself on that. And that is pretty exciting. But a pixel mask really isn't that useful at the end of the day. What you want is an actual network, right? I mean, what Google Maps gives you is a network of roads that you then use for routing. We can get into that more later, what Google Maps does and does not give you. But that's what you want. And so what we decided to do was to actually take another step for this competition for SpaceNet 3, which was, let's take the road network. We've this high quality hand labeled data set of road network, and then ask people to give us that road network back for test images. So not only do we get a pixel mask, we get the actual road network. So this is what I mean by network. It's a graph theory concept. So it's intersections and edges. So the links between different places. How do you actually use that to get from point A to point B? That's what we actually want. So that's the competition we ran for SpaceNet 3. And we were kind of curious how it would go. This is something that's a little novel in terms of asking competitors how to do it. And we actually were pretty impressed with the results. So we had 5 people who had a score of over 0.6 in our metric that we applied. So we call this the apples metric that we developed, average path length similarity. So this is looking at the proposal and the ground truth graph structure. How do your lengths differ when you go from different places? And we can go into a whole different podcast on that. We already talked about it somewhat in previous pods. I won't go into too much detail.
We got time.
Well, yeah, let's just go in deep. Let's get into some graph theory. But scores of over 0.6 were actually pretty surprising. We were pretty encouraged. So it's a multi-step process that you're getting, which is you start with an image. You get actually out a pixel mask to start, which is where you usually would end in previous competitions. So like ISPRS has a segmentation challenge. That's pretty cool. So we acknowledge that there's people who've thought about this before, but taking an extra step of pulling out the road network is what we were excited to see. And that's what people did pretty well. So that second and third step to pull out that network was successful in a lot of ways. 0.6 is not perfect, but it's a good start. And again, especially when you had 5 people that were scored over that, we were pretty encouraged with that result.
And the one thing that's like really surprised me, just even in the last year since we've hosted SpaceNet 3, is I don't see a lot of other evaluation metrics that are kind of driving towards the same result as what Apple's does? I know there's been a few, but I think those still seem in their early stages as well. Is that a fair assessment?
Yeah, I think that there are a few. So certainly to acknowledge there's something that loosely called topo, which is looking at kind of different holes in marbles is the technique they use in a different road network. So that certainly kind of tries to capture the graph structure. And something else that is looking at the number of routes that are within 5% of the same distance. So that is a similar concept. So obviously, appreciate the work that people have done previously to us. But we decided those weren't quite what we wanted, so we had our own, and it's capturing kind of the whole network structure. It works on arbitrary large networks, and I think one big advantage is that it's not really a computer vision metric in the sense that you don't need images to run this metric. You could run it on any kind of data as long as you get a graph structure. So I think it's pretty flexible there. And then of course you have just the pure computer vision metrics, which are very easy to compute. And we do that also in conjunction just to know how we're doing in that sense as well.
Got it. And not to belabor too much on the past with 3, but one thing I wanted to point out was the winning result gave us and correct me if I'm wrong, it gave us a semi-generalized model, correct? It was a single model trained across all 4 cities. And, for us, that's really interesting because so much of this work, right, is hopefully driving towards, whether you're looking at buildings or roads, is driving towards what is called a generalized model, something where you have a model that can look at very different cities, in our case, or geographic domains, without having to train and build new models for each domain. Right, that's really impactful, right? And I think we only had one competitor, right, that did that, correct?
That's correct, at least in the top scoring competitors, right?
Okay, so fast forwarding to kind of where we're at today and what we're talking about. So we saw some pretty good results with 3, and particularly on the generalized side. But then that kind of led to the questions of us internally and all of our SpaceNet partners about what should we be doing next in this domain. So 3 was good, but perhaps didn't get us maybe to where we want to go. So walk us through some of that thought process about saying, okay, what's the next interesting thing in roads that could help be accomplished by some type of deep learning model?
No, it's a good point. So I think the step of going from just pixels to the actual road network was pretty interesting. But all that tells you is like the distances that you want to travel. But there's other features you might care about, right? So pulling out something like the number of bridges you might cross or the surface type. There's a lot of different things. I think the first thing you probably care about in terms of extra features is speed or travel time, right? I mean, ultimately, when you're trying to figure out where to go, how to get from your house to work, you care about usually the time, right? And so it's an extra feature you'd have to stack on top of this algorithm that people developed. And that's what we decided we'd tackle first, because I think that's like the first thing you'd want to know is what's the fastest route. So, and a lot of this was in conjunction to talking with some of our partners here in our collabs, today our partner labs at InQtel, which is in the biology lab that we have. They're looking at pandemic response, and one of the issues is how do you actually respond to a pandemic, say in a poorly mapped area, and pulling out the road network, just the underlying network with just distances is a great start, right? So that motivated a lot of our initial work. But let's say you want to know how best and how to most quickly get supplies and people to an area in need. We really want to know the fastest way, and maybe the shortest method by distance wouldn't help you a whole lot if it's over a rutted terrain or it's a single lane dirt road and you have something that's a mile longer, but it's a highway. That's the route you want to go, right? Obviously, this is something we all understand from using Google Maps, right? And that's something that we've heard a lot to make a little segue in terms of Google Maps, which is there are solutions out there that will help you route, right? Well, obviously, we know this. We use it all the time. And those are great, right? There's some great resources. OpenStreetMap's a great resource. Google Maps is a great resource. There's others as well. Those work well in a well-mapped area in a static environment, right? And what we're thinking is we're not thinking SpaceNet will replace those. Not at all, right? What it will do, though, potentially is if there's a dynamic environment, like you have a natural disaster, or you have, say, seasonal rains in an area that's poorly mapped, And whatever network you have is not reliable for whatever reason. If you need an update to that network, then a pass of a drone or a satellite over an area, if you can process that quickly, which we've shown you can, then you can pull out that network pretty darn quickly. You can get that road network. And then if you can get the speed as well, then maybe you can say, you know what, Red Cross, whomever you're responding, we'll show you this is the best way to go into this village, into this area. Here's how you respond. I think that could be pretty impactful, and I think we have a shot at chipping away at that problem with this SpaceNet challenge.
And I think I can't emphasize this enough. I know you hear me say this a lot, but it's arguably one of the biggest reason why I love this focus area so much, because so many other computer vision problems, particularly in our domain, in the geospatial market, normally what a model is producing, then a human interprets, and that's where you have sort of the final value, right? The value isn't necessarily inherent in whatever the model's producing. In this case, it is. There is no final analysis after that. If you're getting a road route with a projected time, in some cases, if in lieu of any other information, particularly if decisions have to be made quickly, that may be the information that someone acts on. That's really exciting. And I can't believe, you and I have been at this now for 4 years. I can't believe we're almost there in an open source environment. That's really cool.
It's pretty exciting. And again, there are techniques that try and do this as well. Those don't necessarily respond as well if your network is disrupted, right? So the example we use all the time, right, we've talked about this before, is when Hurricane Maria hit, you had to over 2 months to remap the island of Puerto Rico, right? And that was a heroic effort by a lot of people, not knocking it at all. If you can do that faster, it's obviously an advantage. So maybe this automated approach that we're going to attempt, right? It won't be perfect, but if it's a start and it helps you, maybe when you've got people on the ground within 24 hours, if they've got nothing at all, maybe this first pass could really help them figure out how to actually deploy their resources in the best way.
You bet. That's a really good point. I mean, if this ends up in some way, even just informing or helping inform how the hot OSM community incorporates these types of technologies, I think that'd be a huge win for us. So before we get into the specifics of the challenge and what we're going to propose to competitors, we're going to take a quick break, and then we'll be right back and getting into all the good stuff. Geo is hard, and we know that. For the last 4 years, we've been at Cosmic, we've been working on trying to make it just one step easier. And one of the projects that we're really excited about that hopefully achieves this goal or gets us one step closer is what our colleague Nick Weir has produced. It's a project called Solaris. It is a open source software package to help really anyone spin up models that we've open sourced, use their own models, and have them train and test validate against either SpaceNet data or other data sets. And I think it's really cool. And for us, and not only that, we're putting almost all of our work will be integrated with Solaris going forward. The other thing, right, that's coming up is if you're a follower on our blog, which is the downlink with a Q on Medium, our newest member of the team, Daniel Hogan, just put out a pretty cool post on what we've been calling a robustness study on training data, specifically looking at how much data are necessary to build a decent model for building footprint identification. I think this is something that we've been looking at for a long period of time, and it's pretty compelling to start putting some quantitative results against that. And I think it's something that's really unique in the market right now.
Yeah, and I think it speaks to kind of the robustness, to use that word again, of the SpaceNet data set. So we're using SpaceNet data for this study, and I think the results are pretty interesting to show that, there maybe is a limit where you don't actually get a ton more benefit at which point when you keep adding data. And quantifying that, I think, is really important, because there's a lot of things that get thrown around. You hear people throw around crazy numbers like 1 billion examples or 1 million examples. Some cases that's true. In some cases it's really not. Maybe you don't need to spend your entire budget on labeling. Maybe you can spend it on other things and get still a pretty good model out. I think that's important to know.
Absolutely. And so if you're interested in learning more, check out our blog, or feel free to reach out to us, or you'll also find information on all the SpaceNet data and the models we've open sourced on spacenet.ai. With that, let's get back to the pod and talking about our upcoming challenge. Okay, we're back with Adam Van Etten talking about SpaceNet 5, our most recent upcoming competition, part of the SpaceNet series, specifically focused on road network identification, routing, and speed. And so, Adam, let's get into it. All right, so we're building on 3. What's unique about this? So we've talked about time. How are we doing that? And what other challenges are we going to put in front of competitors to make these results perhaps a little more tractable to end users in the community?
Yeah, I think that the incorporation of time, I think, will make this fairly unique. We've seen some decent actually traction as of late with SpaceNet and academic community. So one example is we being the Cosmic team, we're all out at the computer vision and pattern recognition just a few weeks ago, which is one of the leading computer vision conferences in the world. And there was a paper there that was using SpaceNet data, using the metric that we had, and some really cool ideas coming out of using this data to find roads. And so they were just pulling out the road network, right? I shouldn't say just. They were pulling out the road network. Very impressive. But as far as we've seen, pulling out the estimate for travel time is something that's very poorly covered. It's not really been done at all in the academic community. And so that piece alone, I think, will be pretty interesting.
You bet. And one just editorial point. I was not at CVPRs. I was on the other side of the coast. But just to be clear, as we got some good feedback on Twitter about this, I thought about using a deep fake to put myself in the photo with you guys. And I opted not to do that because I was told in quote, it's creepy. So just for the record, I'm not in any of the CVPR pictures.
Well, there's quite a few papers, I think, that would claim to do that. So certainly it'd be encouraged, I think, in the CVPR crowd to try something
I was
of that
tempted.
nature. Yeah.
Tempted. So it's great that we're seeing interest right within the community because that will really accelerate the broader research focused on geospatial. But what are some specific things we're going to do in this challenge? I know we're adding new data. We always get asked for data sets, so that's exciting. But talk a little bit about those data and how we're going to make things just a little bit harder for challenge participants this time around.
I think so. A lot of lessons have been learned in the last SpaceNets. Right, we've run 4 to this point and learned a lot. That's been very helpful. But one, I think. That we've seen, and this is, I think, true largely across the competition sphere, right? There's a lot of data science challenges out there, and it's a really cool kind of concept, right? You get a lot of utility out of it for your money. The one downside is that since these competitions are so well defined, which they must be, it's often possible for competitors to overtrain their models, meaning they know exactly what they need to do. They know their testing data, and they just tweak parameters and add parameters until they get the best score, right? So an example is for SpaceNet 4, we've talked about this in a previous pod, but I'll reiterate that people use an ensemble of 27 different models to get the best score. And you're incentivized to do this because if you can get a 1% increase and that bumps you from third place to first place, you win, right? The problem is if you're trying to deploy this algorithm, 27 times slower is often not worth a 1% boost in performance, right? So this is a lesson that we've learned. Other people know it, right? But we haven't really been too aggressive about it. And I think going forward, what we'll do is we'll just dial back the compute that people are allowed to use significantly. And so if you want to use a 27 model ensemble, great, but you still have to fit it within a very small compute window. Most likely you're not going to do that. Maybe you spend your time doing something like a post-processing, which is still at this point in the geo domain, computer vision and geo, that still is necessary. Like you don't really have end-to-end solutions to go from an image to a graph structure, right? That's that kind of thing. So the post-processing is important, but that's not compute intensive usually. So we're kind of hoping people spend more time there and less time just ensembling a whole bunch of models and really slowing down the compute. So that's one piece. We'll dial that back, what compute people can use. Another is that, especially since the SpaceNet corpus keeps growing, we'll have double digits in terms of cities after this labeling campaign that we're wrapping up now. So by the time this podcast is out, we'll have 4 new cities. But the plan is, in order to kind of address this robustness issue that we just talked about a little bit, is we're going to hold back some of those cities, right?
Whoa, mystery city.
Yeah, a mystery city, exactly.
Yes.
Atlantis. We'll call it Atlantis.
All right, Atlantis. Right? Atlantis it is.
And so by holding that back, right? If you overtrain your model on the cities that we have, so say for SpaceNet 3, right? We had Paris, Shanghai, Khartoum, and Las Vegas. If your model is hyper tuned to those 4 cities, and then you give it a different city, there's a good chance that it will do pretty poorly.
Yeah.
And so this approach will hopefully, in a pretty simple way, right, encourage people to generalize. So that, I mean, ultimately, right, since we're an applied research shop, right, what we want to do is make things that are deployable and useful to the community, right? And if your model only works on downtown Chicago and nowhere else, not that useful, right?
Chicago's a great city, though.
Yeah,
I was born there.
Yeah, and
so,
but
I'm a Cardinals fan. We'll talk about it later.
I don't know. Is Chicago prone to natural disasters? I think it's not too bad, right?
If you count extreme cold for 5 months out of the year, a natural disaster, then yes.
So snow detecting. Okay,
yes,
that. Well, that's a. We have some snow on one of our images. We won't tell you exactly what city yet, but that'll be fun. Actually, that'll be tricky.
And that one's tough.
Anyway, so you want to make sure these models are useful, right? So that's another knob we'll turn is we'll hold something back, and we'll see how people perform on a new city, and I think it'll be marching towards the goal of really making this output of a data science challenge more usable and not something that is hyper tuned. And I'll give an example, right? So there are challenges recently that were pretty cool. Say people were trying to recognize different land types from satellite imagery.
Oh yeah,
and some cool stuff, but the top 50 people were within 1%, I think, of each other for score, which so you have to do some clever stuff to make it top that leaderboard, right? But what we're trying to get at is like, okay, if that's true, great, but maybe if all those are really fast, then that's perfect. Most likely, in those top 50, there's one that's way faster than the other. Probably that's the one you actually want to use, right? So again, kind of just pushing towards something that's more usable is what we're hoping to try with this challenge, along with obviously something cool like pulling out road speed and travel times.
Absolutely. And so the kind of looking ahead, what timelines are we looking at from generally releasing the data set, which is always a big event, kind of like almost a holiday for us at this point. And then when are you generally thinking about launching the competition?
Yeah, so the labeling is getting kind of wrapped up as we speak. So we anticipate releasing that data set kind of in August at some point. And then the competition will launch early September.
Okay.
And it will run for approximately 2 months. So we'll wrap that up around the November timeframe. And then as usual with SpaceNet, where we'll have challenge prizes. So that'll be a cash prize. And there's some other things that might actually go along with this SpaceNet, which we shouldn't talk about yet because it's kind of in the queue, but could be really cool to kind of, increase the incentive to participate and try and win this one.
Yeah, absolutely. So I'm looking forward to pushing some of that information out when we can, and kind of keep your eyes peeled on all of our social media sites, as well as SpaceNet.ai for all that information when we make it available. But with Adam, I'll say this, I couldn't be more excited for 5. It's hard to believe that we're there. I'm looking forward to seeing the results. And as always, great being on a pod with you. Great work.
Really looking forward to seeing what people put out there for SpaceNet 5. I think it'll be great.
Awesome. All right. Well, everyone, thanks for listening today, and stay in touch on all of our sites for more information. Take care.